this video I will be constructing the velocity diagram for question 3 of your problem set. So to solve this I'm going to use set squares, a ruler, pencil, good eraser, a sharpener and of course my calculator. So let's have a look at the question. In the mechanism shown below we have A and B, two equal cranks at right angles rotating about 0.0 at a fixed speed of 40 rpm in the anti-clockwise direction. We're also given the lengths of the various links in mil and we're asked to find the velocity of slider G. In this question we have fixed point at O and then we have two cranks OA and OB rotating clockwise direction at 40 rpm. So our first step, just as before, would be to convert that information into something that we can draw in the diagram. We've also been given a suggested scale and a starting point. 40 rpm, we can find the angular velocity of point AO equals 40 times 2 pi on 60 equals 4.19 radians per second. Converting this using our scale, we'd have to get this in velocity first, so velocity of AO equals 4.19 multiplied by our radial length of the link, converting that to meters as well, so this would be 0.05. Doing this calculation we will get 0.209 meters per second. Converting this with the scale that's given, we can find the velocity of AO, which is equal to the velocity of BO, because they're both rotating at the same speed, is 6.285 centimeters. So that is the length of our two lines. So we can find 2 points to start with in this diagram. We can find point A and point B. Now we need to consider what direction they're going in. So if we're going in the clockwise direction around here, maybe we can see it better on this diagram. If we're going in the clockwise direction, that means our velocity of A and velocity of B have to be going in this direction. So our cranks are rotating anti-clockwise. So the velocity has to be going upwards in both cases. Okay, so back to our diagram, back to our starting point. Can we see them? Yes, we can. So let's start with point A, which is what we do on our previous diagrams. I put my ruler against the link OA. I have my set square along the ruler, and then I have a line that's 6.82 centimeters. Try and get it as accurate as I can. And then so this is A. Then for B, let's write this in, velocity of A relative to O. B, I put my ruler against the link BO. My line is perpendicular to the link, set square along the ruler, and this line is also 6.2. I think I did the other one too long. So let me check. There we go. So this will be 6.28 and this one is 6.28. And they are my first 2 points for this diagram. Let's have a look at our diagram. So A and B. We have A and B are connected to points C and D. So we'll find point C and then we'll find point D and we'll go from there. Of course, if we have new points, we're going to need relative equations. So our first relative equation is going to be velocity of C equals velocity of A plus velocity of C relative to A. So velocity of C is our unknown on the left hand side, velocity of A we know, and we can draw in the line C relative to A because we know point A. So back to my diagram, ruler against the link, starting at point A, and I draw a line. Now I don't know the length of this line or the direction, I just know that the location is perpendicular to the link CA. And then we also have C, which is a slider. So this slider has linear velocity. I'm putting my ruler against the direction of motion, and I draw a line that's parallel to that direction of motion. So I can use 2 set squares for this. So I'm extending this line across, and where these points cross, that is my point C. Point C. So I have velocity of CA, and I have the absolute velocity of C. C relative to A, C relative to my fixed point, and they both correspond to the terms in my equation. So now we're ready to find our next point, velocity of D. This is our unknown on the left hand side of the equation, equals velocity of B, this is known, plus velocity of D relative to B. Again, we're drawing 2 lines, so D relative to our fixed starting point and D relative to B. Here we have velocity of D relative to B, ruler along the link, set square along the ruler, drawing the line. Now we don't know the length just as before, but we do know the location. And then we have another slider, so our ruler along the line, direction of motion, and then we put our first set square in. Let's see if I can do this. And then second set square. Really easy way of doing a parallel line. So where these cross, this is point D, and I'm removing my excess lines and remembering to label as I go. So I have the absolute velocity of D, and then I have velocity of D relative to B. So I have 4 lines now on my diagram. Let's have a look what's next. So I've got C and D. On this link I have E, F and C. So my next point is going to be point E, and then from there I can use a ratio to find where point F is. So now it's time to find point E. This is at the center of the links connected to C and D. So I'm going to write 2 more relative equations. I have velocity of E equals velocity of D plus velocity of E relative to D. Now E is an unknown, D I've just found, and I have the relative E relative to D. And then I have velocity of E equals velocity of C plus velocity of E relative to C. Now I also have point C, and E is also my unknown. So I'm going to draw in 2 lines. I'm going to draw in E relative to D and E relative to C, and where they cross, that's going to be point E. And you can see that from the diagram. The link CE and the link ED are connected. So back to my diagram, I have links CE. So line my ruler along the link, set square along the ruler, and then can you see point C? Drawing a line that goes along my set square. And then for point E, so now for point E relative to D, ruler along the link, set square along the ruler, and then through point D, I'm drawing another line perpendicular to the link, and where these two cross, that is my point E. Again, so important to draw out your relative equations because that told us how we could find point E. So if this is E, I have to draw in my absolute velocity. So this is the velocity of E. I also have velocity of E relative to D, and then I have velocity of E relative to C. So I've got A, B, C, D, and E. Now we can find F. So now we're going to find point F. F, C, and E are on the same link, so we can use a ratio because if they're on the same link, they have the same angular velocity. So the velocity of EC on the velocity of FC equals the radius of EC on the radius of FC. Velocity of FC is our unknown. I'm moving that to the left-hand side, and that will equal the velocity of EC multiplied by the radius of FC on the radius of EC. Now we know the velocity of EC. We can measure it from our diagram. Velocity of EC is about, well, accurately, let's say 5.5 centimeters multiplied by the ratio of the links. Now in the question, we're told that the length CE is 75 mil and that EF equals FC. So that ratio is going to be a half. So if I do this calculation, velocity of FC is going to be 2.75 centimeters. Back to my diagram. So that is the velocity of F relative to C. So from point C, I measure along the line 2.75 centimeters, and this is point F. So this is velocity of F relative to C. I need to draw in my absolute velocity of F. Velocity of F. I'm actually going to move this label, velocity of C, so it doesn't get confusing. Velocity of C. And then all that's left for us is to find point G on the diagram. Once again, a new point requires a new equation. So velocity of G equals velocity of F plus velocity of G relative to F. F we know, G is unknown. G is also a slider. So we're going to draw in two lines, and where they cross, that's going to be point F. So G is also a slider, and if we do the line parallel to the direction of motion, it's actually on the same line as point D, O, and C. So it's somewhere along there. That means we just need to look for a point of intersection once we do the line perpendicular to the link FG. So ruler along the link, set square on the ruler. From point F, I draw a line. Where does it cross our slider velocity? This is point G. Remember to draw in the total velocity of G and the velocity of G relative to F. Okay, and that is your completed velocity diagram for this question. So if we're asked for the velocity of G, you measure the line from your fixed point, starting point to point G, and remove the scale. So in our next video, I'm going to go over the acceleration diagram for this question. Once again, this is one of the harder velocity diagram questions, so it's excellent revision, but you wouldn't be expected to do this by yourself.